The Sun. Perhaps you recognize it. Long thought to be a hypothetical object by residents of Tacoma, the Sun has been observationally confirmed by astronomers and determined to sit a distance of 1.5 times 10 to the 11th meters away from Earth, our home. We can actually determine the temperature of the Sun comfortably from Earth as long as we make a few simple assumptions and take one simple measurement. So, we have to assume that the emissivity of the Sun is epsilon of about 1. The emissivity tells you how efficiently something radiates. The Sun is famous for its radiation, and epsilon of 1 is approximately right for the Sun. We also need a measurement that the intensity of solar radiation at Earth is about 1.36 kilowatts per square meter. So that tells you how much radiation is actually spread out over a square meter. That's a little tougher to measure directly. You can estimate it just by putting your hand out on a sunny day, but then you have to account for things like the fact that the clouds reflect some light. This is a pretty decent estimate of the solar radiation that actually hits our atmosphere, though. Finally, you need the radius of the Sun. That's pretty easy to get as long as you already know the distance of the Sun. The Sun is about half a degree in diameter in the sky, so you can translate that to a size of its radius of about 7 times 10 to the 8th meters. So we can use this information to figure out the temperature of the Sun, believe it or not. And the way we do that is to use the Stefan-Boltzmann relation. So Q dot E equals epsilon sigma A T to the fourth. Just to review the terms in this equation, so Q dot E is the power radiated from a thermally emitting object. Something like the Sun is radiating thermally, by which I mean that it's radiating as a result of its temperature. That's where the Stefan-Boltzmann relation applies. If you have something like a big LED light instead of the Sun, the LED light does not reach the temperature that corresponds to the radiation we get from it. LEDs don't work by thermal radiation. Likewise, if you're wearing a blue shirt, it's not blue because it's like 10,000 Kelvin, it's blue because it's reflecting blue light. So you have to keep that in mind when applying this equation. It only really applies to situations where the radiation being produced is as a result of the object's temperature. The other terms, well, epsilon we talked about, sigma is a constant, A sun is the surface area of the Sun, and T sun is the temperature of the Sun. And that's what we want to solve for, so we can rearrange this to solve for the temperature of the Sun. That's fairly straightforward. About that area, well, A sun is the surface area of the Sun. It looks like pi r squared the way I drew it, but of course the Sun is a three-dimensional object, so its exterior surface area is 4 pi r squared. So we can plug that into the relation for T sun. Looking at this expression, we have all of the variables except Q dot E. Q dot E is not the same as the intensity, but they're related. So Q dot E is the Sun's total power in watts. What we measure, however, is the intensity, which is in units of power per area. So we need to relate those two. This may be a relationship that you learned in introductory physics. If not, it comes up every once in a while. I would probably help you through it in this class, and that is that the intensity is proportional to the power divided by the area over which that power is being distributed. So at the distance of Earth, what is the relevant area over which the Sun's power is being distributed? Well, the Sun's power at the location of Earth is being distributed over a sphere, that is of course imaginary, that is the size of Earth, so it has a radius equal to the distance between the Sun and the Earth. So we can rewrite that area term in the intensity expression to be 4 pi d squared, where d is an astronomical unit, 1.5 times 10 to the 11th meters. Okay, if we do that, now we can rearrange to solve for Q dot E. So we do that, and our whole point in doing this was so that we could substitute back in for this expression up here with this expression down here. So let's move things up and put it into the equation for the temperature of the Sun. Alright, now we have an expression where we know all of the variable values. So let's substitute in the numbers. We have all of the numbers that we were given in the problem, and sigma, the Stefan-Boltzmann constant, you just have to look up. It's 5.67 times 10 to the minus 8th watts per square meter per Kelvin to the fourth. Those units are actually important insofar as you need to make sure you're working in watts and meters, and that if you're solving for the temperature, you know you're going to get out Kelvin. So let's simplify this by one line, and now you can see that the units of watts are going to cancel out. You have 1 over Kelvin to the fourth raised to the 1/4 power. That'll get you Kelvin out. So the answer, after doing all that math, is that the temperature of the Sun is 5,760 Kelvin. That's technically the temperature of the photosphere where the Sun's light comes from that reaches us. That's a really accurate estimate. In fact, this is one of the standard ways to estimate the temperature of the Sun. You try going there with a thermometer, you have all sorts of problems. If you use the Stefan-Boltzmann relation, you get a very accurate estimate of the temperature, and all without having to leave the comfort of your own home.